Let's take a look at an example of energy conservation. Suppose you place your game console on a frictionless sloped surface. It's initially at rest, but it speeds up as it begins to slide. Using conservation of energy, let's determine its speed at the bottom of the slope. If the energy is conserved, there are many ways we can write this down to give us a starting point. For example, this expression tells us that if the kinetic energy increases, that is, the change in kinetic energy is positive, then the change in potential energy must decrease by an equal amount. When we write out the four energy terms, remember that the console starts from rest. Also notice that the two potential energy terms combine nicely, which goes to show that the initial and final positions aren't so important. What really matters here is the change in height, delta y. So energy conservation gives us a way to determine the final speed of the object, as long as we know how far it has moved. Now, in some cases, the energy is not going to be conserved. This happens whenever work is done to the object. If positive work is done, this adds energy to the system. We can account for this by equating the work done to the change in energy. If W is positive, then the final energy will be greater than the initial. And if W is negative, well, then E final must be less than E initial. Suppose we account for friction between the console and the sloped surface. If we overlay a free body diagram, we can see that the friction force points in the opposite direction to the displacement. The angle between friction and displacement vectors is 180 degrees, and the cosine term in our calculations then gives us a value of -1. Negative work will be done here. As the console slides down the slope, some of that potential energy is drawn out of the system by the negative work done. Therefore, the final speed will be less than what we found earlier when friction was ignored.